Hello, my name is Rahul Gopinath, and I am an incoming faculty at the University of Sydney, Australia. Currently, I am at the CISPA Helmholtz Center for Information Security, Germany. And with me, I have Rafael Retra, who also works in CISPA in the same area. Rafael will be talking about our recent innovations, and later I will outline the current research. In particular, about how you can build an ecosystem of pluggable, composable, and completely automatic fuzzers. Over to you, Rafael.
Thank you. So as we have already seen, for example, in the talk from Tuan, we know how feedback-directed fuzzers work and that they can be really effective in finding important bugs and vulnerabilities. But most of those fuzzers are completely agnostic to the specific structure and format of the inputs that they're mutating or generating. And this can lead to some problems. So for example, most of the mutations that AFL would perform on an input actually make this input invalid, which can be useful for finding syntax errors and parsing bugs in programs, but also makes it harder to go deeper into the program execution and find more meaningful semantic bugs. Another problem here is that the performance of the AFL will be highly dependent on the particular corpus of initial inputs that we use. So for example, if there is some feature such as one specific chunk type, which is never present in any of the inputs in the initial corpus, it will be really hard for AFL to synthesize a new input that will have this particular feature. And another problem here is that we're always relying on feedback from the program. So this is not readily applicable in black box settings where we don't have feedback available. Now, what if we could build a format-specific fuzzer? So a fuzzer that specializes in producing, for example, valid PNG files. How would you go about generating a new, completely random PNG file? Well, one approach is to read the formal specification and implement such a new PNG fuzzer from scratch. But those file format specifications are generally dozens or hundreds of pages long. They are not machine readable, and it would take really a long time to write such a format specific fuzzer from scratch. And also the effort needs to be repeated for each new format that you want to support. But is there a simpler way to understand a file format such as PNG? Can we inspect and get insights into the format just by looking at the file? Well, if we open a PNG file with a hex editor, those bytes are pretty incomprehensible. But actually, if we use the 0-on-0 editor, this editor is actually able to parse the file and shows us the structure of the PNG inside it, showing all the different chunk types and the fields inside of each chunk. So how can this editor obtain this information? Well, it is using a file format specification, which it calls a binary template. And now, inside this binary template, we actually define all the structure in the file, for example, the chunks. And here, a PNG chunk, for each variable that we define, we're actually parsing the corresponding number of bytes from the file. So for example, the first 4 bytes in a PNG chunk are the length field. And the next 4 bytes are the chunk type. And then we have some amount of data. And the amount of data we have is actually given by the length field. And finally, we finish with a CRC code. So here we can already see that we have properties which are context sensitive, such as those variable length arrays, checksums, So those formats can be pretty complex and are not easy to handle with simpler formalisms such as a context-free grammar. Now, the language of binary templates also allows us to define so-called local variables, which are variables that don't actually parse bytes from the file, but they can be used in arbitrary computations. So we can, for example, compute the actual checksum of one PNG chunk and compare it with the value we find in the CRC field to see if the checksum is valid. And those binary templates, they're pretty complete. They don't just show arbitrary data inside of a chunk, but they actually have information about the correct structure of this data based on the chunk type. So we can have conditionals that say, for example, for the IHDR chunk, the structure of the contents should be given by this PNG chunk IHDR, which is another struct defined in the same PNG binary template. Now, the good news here is that there are more than 200 of those binary templates available. They're publicly available on the 0&0 editor website, and they have been developed over decades by several contributors. And so this brings the question, could we use the format specification contained in those binary templates to produce a format-specific fuzzer, such as a specialized PNG fuzzer? Yeah, and the good news is that we can. We have shown in Format Fuzzer that actually for several different popular formats, we can produce effective generations from such binary templates. We just need to make a few simple changes. For example, when we are going to choose the value that a certain field will have, for example, the CRC field here, we may need to specify what are the possible values that this field should have. For example, in this case, it only has one sensible value, which is the CRC value that we just calculated before. Or when we are generating the length field, we could specify, for example, a range of feasible lengths. For example, minimum 1 byte, maximum 16 bytes. But sometimes we don't know the length that this chunk should have before we actually generate the data in this chunk. So what we do is that we use this initial length value just as a hint. Then we go ahead and generate the data in the chunk. And after we generate the data, we can go back and fix the length value if necessary. And also, for example, for the chunk type, there are some restrictions on what is the correct order of different chunk types in a PNG file, but we can incorporate those into the binary template by specifying two lists. One list of the mandatory chunks that need to appear, and another list of all the possible chunks that can appear at a certain position, so that we will eventually generate suitable chunk ordering, which is valid according to the PNG specification. So our tool, Format Fuzzer, it is able to take one of those enhanced binary templates, such as png.bt, and automatically translate the binary template into C++ code that can efficiently parse or generate PNG files. And here, when we are making decisions during the generation of a PNG file, we use a so-called decision seed. What this means is that every time we decide what value a given field should have, or which type of chunk we should generate next, we sample some random bytes, and those come from an array of bytes called the decision seed. And we can actually do the reverse. And when we're parsing a PNG file, we can recover which decisions we would have to make in order to generate the same file. Now, why are those decision seeds useful? They can be useful in our implementation of smart mutations, for example. So those smart mutations are mutations we can apply to the files that preserve the structure of the file. For example, we could pick one chunk inside of a PNG and abstract this chunk, which means we're going to replace this chunk with a fresh, completely new random version of the same chunk type. And this is only possible because we're both able to parse and generate those files. We can also replace this chunk with another chunk of the same type from a different file. Or we also have smart insertion and smart deletion of optional chunks from those files. Now, the smart mutation operations from Format Fuzzer, they actually operate over the decision bytes and not directly by just copying bytes from the file. And the advantage of working over decision bytes is that we can respect the contextual information in the mutated file. For example, if instead of mutating one whole PNG chunk, we just mutate the contents inside the chunk, for example, the PNG chunk IHDR contents, we could replace those contents with different contents or even a different length. And since in our binary template, after this data, we compute the correct checksum and we fix the correct length, the mutated file will have the correct checksum and length, even if the content and length has changed inside the chunk. So how can Format Fuzzer be used, actually? It can be used standalone, but it can also be integrated into existing fuzzers, such as AFL. The simplest way to use Format Fuzzer is as a black box generator, which simply generates new files for fuzzing from scratch by making random decisions. But Format Fuzzer can also be used as a black box mutator. Here, we would take a corpus of existing PNG files, we parse all those files to get information about their chunks and obtain the corresponding decision seeds, and then use those to apply smart mutations and get new files for fuzzing. But the best approaches actually are the ones that incorporate the coverage feedback that you would get from a fuzzer such as AFL. And there are actually multiple ways that Format Fuzzer can be integrated into such a format-agnostic fuzzer. One way would be to use AFL to mutate decision seeds. Yeah, so as I was saying, this was the approach where AFL mutates decision seeds, which are then fed into Format Fuzzer. So this is a generator-based approach of using Format Fuzzer. But yet another approach is to use Format Fuzzer to provide smart mutations to AFL. So here we allow AFL to implement its original random mutations over the files, but for each file in the AFL queue, we also parse this file with Format Fuzzer to obtain information about the chunks and the corresponding decision seeds, and use those to apply smart mutations so that we can generate high-quality valid files for fuzzing. So in our evaluation of Format Fuzzer, we noticed that supporting a new file format takes much less effort than it would take to write such a format-specific fuzzer from scratch. And in terms of speed, the generation and parsing is pretty fast. We can generate thousands of files per second so that Format Fuzzer doesn't become a bottleneck if it's integrated into an existing fuzzer such as AFL. And in terms of accuracy, most of the generated files will be considered valid by the target application. In terms of fuzzing results, we have seen that consistently for most benchmarks and file formats, this integration of AFL with Format Fuzzer will help us cover new lines of code. And this will also help us find new bugs. So we have reported dozens of new bugs into FFmpeg and Timidity. And to this date, 8 distinct bugs have already been fixed by the FFmpeg developers. Yeah, so we are happy to announce the first release version of Format Fuzzer today, which includes the integration with AFL++. And here you can find more information in our project page, the source code, and our preprint paper. And now I'm giving back to Rahul.
Thank you. Okay. Thank you, Rafael. You have seen how to use Format Fuzzer to fuzz programs using XSD binary specifications. And you have seen how useful they can be in practice. We will now look at some of the very recent research that we have been doing in language-based fuzzing. Each of these represent a key breakthrough that can improve the effectiveness of fuzzing and improve the life of the fuzzing professional. Given the lack of time, however, I'll be focusing on 3 key technologies that are available today and can help build the next generation of fuzzers. We start with mining input formats. From Rafael's talk, you already know that if you want to get past the parser and reach the core, you need the input format. Otherwise, all you have are syntax errors that prevent you from reaching the core. For this talk, I will be working with JSON as an example because it is one of the most widely used input formats and everyone understands it. So now what is an input format? An input format is simply a description of what a valid input looks like. And Format Fuzzer, for example, uses 101 template formats of the programs that it fuzzes. In our research, we require a bit more formal specification. So we build our techniques on top of context-free grammars and then later adapt it for the more context-sensitive Format Fuzzer approach. That is, we will make use of the context-free grammar of JSON specifications as the input format. But fear not, you will not have to write a grammar by hand. So here is the JSON grammar that is a context-free grammar. And a context-free grammar is just like a procedure definition in programming languages. We have a number of keys and associated definitions. And each definition contains multiple expansion rules. And each expansion rule defines one way to expand the non-terminal and contains terminal and non-terminal symbols. And each non-terminal symbol in turn has their own definitions. Terminal symbols are simply basic alphabets of the input. And such grammars represent the input language in that any input can be represented as a sequence of application of the rules in the grammar. And we call such constructions the derivation tree or the parse tree. More importantly, given such a grammar, writing a grammar fuzzer is really simple. You can write a very simple grammar fuzzer in about 15 lines of Python, and you can customize such fuzzers to any extent you want. What else can you do with a grammar? If you have valid seed files, you might be able to make use of them better if you separate them into components first. That is, you need to parse these seed files. Now, most of us think of parsers as a very complex piece. But a parser is just a grammar fuzzer turned inside out. And you can write a simple and fairly complete parser in another 15 lines of code, as you see here. Given both a parser and a fuzzer, you can now make use of the existing seed files and combine features from different files to reach deep into the program logic using valid inputs. But this leaves a question. Where can we get a grammar for the program being fuzzed? Can we rely on a formal grammar being used for parsing by the developer? The trouble is that almost everyone hand rolls their own parser. and they almost never start from a formal specification. And another problem is that even when they start from a non-specification, most parsers do not implement the specification correctly. For example, here is the JSON parser header file for Chromium. And notice these incompatibilities from RFC in the header file. And here's another example. This is JSON parser for Python. And you can again see that Python doesn't implement the RFC exactly. In particular, see this highlighted portion. The implementation is actually a superset of RFC. That is, even when a programmer starts with a formal specification, it is often used as the minimum of what the program should accept, with numerous extensions that may be intended or unintended. This means that if we start with a documented specification for fuzzing, our fuzzer's reach may be severely restricted because we can't produce inputs that correspond to these extra features. So the question is, how can we get an accurate grammar? Our key idea is that handwritten parsers that are written in a recursive descent fashion already encodes the grammar in their control flow. For example, given the JSON parser, you can extract the specification directly from the parser by first extracting the control flow graph. And then this control flow graph of the program can be directly represented as a context-free grammar. That is, a sequence of operations become a rule, the branches of a conditional becomes alternative rule expansions, and loop iterations become recursive non-terminals. To convert this grammar into the input grammar, we use a set of sample inputs. Then we trace the execution of each sample in the program, and each characters in the input are assigned to the non-terminal corresponding to the control flow node that accessed it last. And this works really well. We use this approach for our paper at FSC 2020. And our evaluations show that we were able to obtain really good grammars with high precision and high recall. That is, we can rely on our technique to produce grammars that cover most of the actual input features of the program. Now, we can mine grammars from programs if we had sample inputs. Where can we get these sample inputs that cover all features? Turns out you can use the same machinery for grammar mining to actually generate samples too. Remember that we track which characters were consumed at which nodes. What we do is to start with some input, find where the parsing failed, and provide the character that would let the parse continue at that point. And proceeding in this fashion gets us longer and longer inputs, which at the end gets accepted by the program, giving us the unbiased samples that we need. That is, you can combine sample-free generators with Mimit, producing an automated grammar miner. So what does this mean for you in practice? With Mimit, you can extract an accurate input grammar of the program that you want to fuzz. The technique is language agnostic, and it is easy to use. And the grammar that you mine can be used by any fuzzer, and the project is available as open source. So we have seen how to automatically mine the input format. Let us next look at patterns of failure. During fuzzing, you may often produce crashes. And the problem is that inputs that induce failure in the program under test can be really huge. And it is almost impossible to understand from an input what precisely caused a crash, what part of the input was responsible for the crash. And one way to get a handle on the situation is to minimize the crash-inducing input. And the standard technique here is delta debugging. But given that we have the input grammar, we can apply a more effective technique called grammar-based delta debugging that minimizes the input to the smallest possible input that still causes the crash. That is, in our case, the failure can be reproduced by the 7-character input. However, while this new input is tiny, it still gives no indication to the developer as to the cause of the crash. For example, this input doesn't tell us if the crash happens on any input that is larger than 6 characters, or if the empty key is important, or if the empty array is important, and a number of such questions. So, can we do better? Can we identify what precisely caused the failure? What part of the input was responsible for the failure? This is what we tackled in our paper at ISTA that introduced a technique called DD-set. With DD-set, the idea is simple. We start with a parse tree of the input, and the idea is to find nodes in the tree that can be replaced by a random value of the same kind without affecting its ability to induce failures. In our example, the string can't be abstracted, but ELT can be abstracted, and this gives us the abstract representation of the input, a simple object with an empty key and any element as its value. And this gives us a concise pattern that immediately tells you where the failure occurred in the input. In this case, the failure occurred because of the empty key. So this works on simple JSON inputs. What about the real world? And this is what we looked at. And these are issues from real world projects. Each of these are real world minimized test cases for bugs in 2 different JavaScript interpreters that caused a crash. These are from Clojure and Rhino. And if you look at these minimized test cases, it's not exactly easy to get an idea of what is the essence of the bug, what caused the crash. Now look at the abstract input. And you can immediately see which parts of the input are essential for reproducing the bug. And this abstract input is not just useful for understanding what parts of the bug is important. You can actually use it for fuzzing. That is, you can embed the particular failure pattern that we just mined into our grammar, producing a new failure-inducing grammar that we call an evocative grammar. With our new evocative grammar, you can now produce an infinite number of inputs, all producing the same failure. And we also provide a few statistical guarantees about the grammar that we construct. Now, these are statistical because it depends on the accuracy of the input, the pattern that we mined. The grammar that we produce by embedding can produce each and every instance of the failure-inducing pattern. So what does this mean for you in practice? Given that any interesting behavior of the program where you have at least one input that can induce the behavior, and this behavior can be a crash, or it can be a coverage of interesting methods, or it can be consumption of specific resources, or not. Given one such input, we can abstract that input into its essence. And then we can use this abstract input to produce any number of inputs, all of which will contain the failure-inducing fragment. And you can use that particular grammar that we produce on any grammar-aware fuzzer. That is, if you are a developer and you have a test case that induces a failure, you can generalize that test input and check if your fix works under all circumstances. If you are a fuzzing practitioner, you can quickly check whether a historical bug has been fixed in all contexts. So now we have seen how to extract patterns of failure and use them to build focus fuzzers. Let us next look at how to compose such fuzzers together. We saw how to produce evocative patterns. Now the next question here is, what if there are more patterns? That is, say we have another crash that happens when the JSON string contains a key with a value of null. And you can have another pattern that represents this crash. We may want to generate inputs such that both conditions are satisfied. That is, the JSON fragment contains both an empty key and a key value of null. On the other hand, we may also need inputs such that it triggers the empty key, but null values are guaranteed to be absent. Or we may also want to avoid triggering the crash by guaranteeing that neither patterns are present in the input. The interesting part here is that each of these operations are possible with our patterns. We can now produce grammars that correspond to each of these specialized requirements that are usable by any grammar-aware fuzzer. For example, here is a complete grammar that is equivalent to the combination of expressions. That is, input should contain an empty key, but should not contain a null value. And note that the specialized evocative grammar is a simple context-free grammar. That is, this grammar can be fed into any grammar fuzzer, producing expressions which are guaranteed to contain at least one empty key and no null key value. And we saw how we can abstract different bugs in different interpreters. Now the trouble is that new bugs hide between feature interactions. So ideally, we want to produce inputs that contain more than one fault pattern. So using our expressions, we can now produce inputs containing both closure bugs, inputs containing both Rhino bugs, or pick one Rhino and one closure bug for fuzzing randomly, or first further ensuring that none of these bugs are triggered in each input that is produced. That is, using our technique, we can completely tame grammar fuzzers into producing exactly what you need. Here's another example. The behavior that we look at doesn't need to be crashes. You can also abstract any behavior. For example, say we have this application. Assume that you have an input that covers a method, and you can abstract the input to produce an evocative pattern. And this evocative pattern will produce inputs that are guaranteed to have the role admin and hence cover the assign admin rights method. Then consider another input that covers another part of the code. Here, the modify DB method is covered if the remove table API is present. As before, you can use the evocative expression to produce an evocative grammar that is guaranteed to contain the given pattern. What if you want to produce inputs that cover both parts of the code at the same time? You can do that with evocative expressions and produce inputs that may be unexpected by the program. Or you can look for behaviors that should never happen. The grammar that we produce by evocative expression can produce each and every instance of the failure-inducing pattern, looking for very, events with very little probability. And there are other uses for evocative expressions beyond generating simple strings. For example, for fuzzing API structures, you may need to produce complex data structures. And the algebraic data structures can be represented as a context-free grammar, at least some of them. And we can use evocative patterns to generate data structures with specific properties. Again, if you have data structure in the memory of the program, you can also use these evocative expressions to search for specific patterns. Now, this is currently limited to non-cyclic structures, but we are working to remove that limitation. So let us take a step back and see what evocative expressions can be used for. You can mix and match any number of behaviors that you want in a fuzzer. For example, say you have an application that consumes XML, like what Madeline mentioned. And you want to fuzz this with an XML parser that produces inputs with a Rust vulnerability. And you can produce and an SQL injection vulnerability. And you want to avoid triggering a non-bug B and do not want to cover a function A. And you can produce a fuzzer with this particular formula using evocative expressions that precisely matches what you want. Each of the inputs that you produce from the grammar will follow all these restrictions. And the grammar that we produce can be consumed by a fuzzer like cats if it is grammar aware. And it may be coverage or no coverage of particular functions, consumption of particular resources, crashes, or any behavior. The only constraint we have is that you have an input that induces the behavior. Provided you have such inputs, you can abstract the behavior automatically and mix and match any number of behaviors, all without writing a single line of code. And this was published at ICSE 2021. And I also have a series of posts introducing various aspects of evocative expressions. So what does this mean for you in practice? I have shown you how you can produce specialized fuzzers that target specific behaviors. And you can now mix and match such specialized fuzzers producing complex behaviors without writing any code. With all these capabilities, we envision an ecosystem of refined fuzzers where you have evocative expressions that are curated from historical bugs, interesting behaviors, and likewise, very similar to the regular expression databases that exist today. That ends my part. Over to you, Rafael.
Yeah, and as current and future research we are also looking into applying those really great research ideas from Rahul and incorporating them into format fuzzer, such as being able to mine a binary template from analyzing program execution, or debugging failures by minimizing and abstracting inputs. And we also have a lot of new interesting research directions, such as fuzzing really complex formats such as digital certificates. But in the interest of time, I think we should finish now, and Rahul and I will be happy to answer questions.